And we'll go ahead and get started. So welcome everybody. This is the May meeting for the Tucson astronomy, amateur astronomy fundamentals group. My mouthful, my mind's all over the place right now.
A little louder.
Might be too quiet, Doug?
Yeah.
Let me see if I can fix that real quick. If it is it still really quiet? If okay.
Yeah.
Let me go grab another headset. I'll be right back. Was not what I was expecting. Plan B. One moment. You guys hear me now?
I don't know if it's much better.
Okay.
But okay, I can hear you.
Nope, just had to change headsets. But too many things.
That sounds good.
So restarting. So welcome to the May Astronomy Fundamentals meeting for the Tucson Amateur Astronomy Association. Tonight we have one presentation and one demo / something I wanted to show off based off of a project that I was doing for an engineering course in school, which may be of interest to you all. So tonight, Doug will be starting off with the presentation on telescope collimation. And I think I need to give you the presenter permissions, Doug, when I remember how to do that. Make co-host. And whenever you're ready, Doug.
All right. Let me see if this will work. Okay. So far, so good. Okay, that worked.
And I can see it.
I have to get rid of that. Okay. Yes. Over here. Okay. All right. So I'm going to give a brief talk about how to collimate your telescope. I think this is something every amateur astronomer who owns a telescope should learn how to do. So I'm going to give a little talk on it. Of course, I have my humor slide, which I put in all my presentations. Hey, Connor, does this look about right?
Within which field of engineering or science?
Astrophysics.
Yeah.
I remember things like that when I did graduate work. Okay, so what is collimation? Well, the definition of collimation, right out of Wikipedia, is the process of aligning all the components in a telescope to bring the light to best focus. Every telescope needs to be collimated at some point. Okay, that being said, actually, collimation is usually broken down into two different areas. There's optical calibration and there's mechanical calibration. Now, optical collimation, which is what I'm going to talk about, is where you line up all the telescope's optical surfaces, essentially, to bring the image to the correct orientation in the focal plane of the telescope. Mechanical collimation is aligning the physical components of the scope. Like the focuser needs to be square on the tube, and the mirror needs to be centered in the tube, and the secondary mirror needs to be aligned with the primary mirror, optical axis, and so forth. I'm not going to spend any time on mechanical collimation, mainly because mechanical collimation is usually done at the factory when they put your telescope together. They usually make sure that the mirror is centered in the tube, and they usually make sure that the focuser is square to the tube, and they usually make sure that the secondary mirror is lined up and tilted at the right 45-degree or 90-degree angle, whatever is required. And unless you bang the scope around a lot, you probably don't have to adjust the mechanical collimation ever. It's very rare that you have to mess with those elements in that sense. I think in all the years that I've owned telescopes, I've only had to do a mechanical collimation once. And that was because I literally dropped the telescope on the ground. So some basic stuff here. We talk about 3 types of telescopes. There's refractors, reflectors, and catadioptrics. And then there's subtypes. There's 2 types of reflectors that we usually talk about, Newtonian and Cassegrain. There's also a third one, Gregorian, but Gregorian is basically just almost the same as a Cassegrain. And then in terms of the catadioptrics, there's the Schmidt-Cassegrains and the Moxitovs. There might be others, but those are the main ones. Now, what I'm going to talk about first are the 2 subtypes of telescopes where optical collimation should never be tried by the owner, should be handled literally by experts. In fact, these 2 types of telescopes, there is no way for you to do the optical collimation. That's why you take it to the experts and let them do it, because that usually requires taking the telescope apart. Well, refractors. So this is the typical refractor telescope. It's got a 2-element objective lens called a doublet, which is typical for the low to mid-price refractors. Higher price refractors can have 3 or sometimes 4 elements in the objective lens. These lenses that make up the objective are usually cemented together, or they're mounted in a lens cell with spacer tubes between them or whatever, but that whole lens cell makes up the objective to the telescope, and that's usually optically collimated like in the factory when they do the mechanical collimation. The lenses all need to be lined up and properly spaced and everything, and that's all usually built into that lens cell. And there's no usual, it's if the lenses are cemented together like they often are, there's really nothing you can do in terms of optical collimation. There's unless you break the lenses apart or something and damage them. So if optical collimation ever does become necessary, it's time to go see an expert, because it's usually beyond the means of most people to do. The other one is the Moxitov. It doesn't have a secondary mirror. All it has is a silver spot on the inside surface of the corrector plate. The corrector plate is mounted in a cell, just like the objective lens on a refractor. And usually the mechanical collimation, that is lining up the corrector plate in the tube so that it's at the correct distance and everything from the primary mirror, that basically handles the optical collimation issues also. So unless, again, the telescope is seriously shocked or damaged, Maxitovs usually hold their optical collimation really well, usually for the entire lifetime of the telescope. I've got a Moxitov telescope, actually. And I did have to have it recollimated. I had to take it into Stellarvision and let Frank get in there to the guts and recollimate it, because I did something rather dumb. I didn't drop it, but I left it outside during the summer in a sealed container exposed to the sunlight. And the heat did something to it to where it was out of collimation. And the telescope, in the case of a Moxitov, in the case of a refractor, you can usually unscrew the mirror cell and at least get to the mirror cell. I'm sorry, the lens cell, the objective lens. That whole cell usually can be unscrewed out of the tube, so you can at least get to the optical components if you do want to do anything. But in a Moxitov, there's almost no way to get to the internal components without literally taking the telescope apart. So when my little Moxitov stopped being collimated after being out in 120-degree heat in a sealed container, which I will never do that again, I had to take it to Frank, and he literally had to take the telescope apart to get to the insides, because that's the only way you can adjust the main mirror and everything else in there. And that was a lesson, a painful lesson that I learned. That Moxitov is now stored in the house all the time. But these are the two types of telescopes where optical collimation is usually never required, because usually they hold their optical collimation for as long as you own the scope. Now, so a lot of amateur astronomers, you say the word collimation to them and they run away and hide. They think this is a difficult procedure, and they're scared to touch anything related to the optics. In reality, this is not a difficult procedure. And in fact, usually for most telescopes, it's less than 5 minutes to do. I check the collimation of every telescope I use every time I take a telescope out to use it. When I go to a star party and I set up my Dobsonian, first thing I do is I check the collimation. It's very easy to check, and it's very easy to adjust it if it needs adjustment. They sell a lot of gadgets out there that will assist you in the collimation process. They sell collimation eyepieces. They sell laser collimators. There's a whole list of things that you can buy to help you do the collimation of your telescope. Frankly, I think they're a waste of money, but that's just my personal opinion. Some people may like them and use them. I don't, and I won't recommend them. I won't necessarily. I won't criticize anyone who does use them. If they work, that's great. That's fine, but I just don't. I don't see the need. So the procedure I'm going to talk about is what we always call the star test. Very simple, and it works. So the procedure is real simple. When you take your telescope out, you point it at a bright star. The brighter, the better, because you get a better look at the pattern. Sirius is, at this time of year, still available to use. Vega in the summer, whatever bright star you can find. Usually, you just point the telescope at the star. I use a medium power eyepiece, something that gives me about 100 power, like a 20-millimeter eyepiece with my 2,000-millimeter focal length telescope gives me 100 power. I use a medium eyepiece like that, and I would recommend you do. Some people say use a low power eyepiece. Some people say use your lowest power eyepiece. But I think if you do that, you end up having to switch to a medium power eyepiece to get a better collimation, if you like. You could get pretty good with the low power, but the higher power you can go, the better your collimation will be. So I start right off with a medium power eyepiece. Anyway, you get your medium power eyepiece in your telescope, you put it on a bright star, you center the bright star, and I should have said that somewhere. I did. Center the bright star in the eyepiece. And then just defocus the star, either in or out. And you'll get a pattern that looks like that pattern on the left or one on the right, where you see the rings and you'll see the shadow of your secondary mirror in the middle. If you've got a Schmidt-Cassegrain or a regular Cassegrain reflector, there's no spider veins, so you'll just see the round secondary shadow in the middle. If you've got like a Newtonian telescope with spider veins, you'll see the shadow of the spider veins, like in that image on the right. It is a 4-vein spider, for example. But what's important are the rings. You'll see those rings. And it doesn't matter whether you go in or out. You should see the same pattern or a very similar pattern in either way. And what you want to see is that the rings are all evenly spaced all the way around, like the images down in the bottom left. That's the type of pattern you want to see. Or either of the images up top are actually pretty good. The rings are evenly spaced in both of those. That's what you want to see. Now, this image is a circular image, and that's because your mirror is circular. If you've got a mirror that's not circular shaped, like the James Webb telescope, and he talked about that at the presentation, where it gets a very funny shape for the star image because the mirror is not circular. But I've actually seen amateur telescopes where the mirror was square. And in that case, you wouldn't have a circular pattern here. You'd have a square pattern, and the rings would not be rings. They'd be a series of squares. But again, what you want to see is they're evenly spaced all the way around. So step 3, if you look at that pattern and the rings are evenly spaced all the way around, you're done. Okay. What that means is that when you focus in on the star, it'll focus to a really nice little pinpoint, and you're done, you're ready to go, you're collimated. Now, if the pattern is not evenly spaced, and if you look at this image on the right, let's see, where's my, okay. And if you look at these figures here where it's showing the rings are not evenly spaced, like this one and this one, okay, then that means you're out of collimation. And if you were to focus down on your star, you wouldn't get a nice image like that. You'd get something that looks like this over here. Okay, so you're not collimated. All right, so that means you need to adjust your collimation. How do you do that? Okay, that's what we're going to talk about. There are collimation screws on your telescope, no matter what type of telescope you have, and I'll talk about how you find these screws. I say locate the collimation screw that's closest to where your rings are closest together. So what you want to do is you want to find a collimation screw that's closest to this area where the rings are really close together. Okay. And the way you do that, the way I do it is real simple. I'm going to turn the light on here. And let me see. I'm going to stop sharing for a minute, or wait a minute. Yes, I'm going to stop sharing. So what I say here is you take an object. I use a pencil or a chopstick, and you hold it over the front of the telescope. So let me demonstrate that. So I'm going to stop sharing. So can everybody see this guy?
Yes. Yeah.
Okay, so this is the top of my Dobsonian telescope. So I'm looking through the eyepiece right here. Okay. And I'm looking at my bright star, and I see that the images not perfectly collimated. It's out of collimation. I'll take this pencil and just put it over the front of the scope like that while I'm looking. And I'll rotate it around like this until, because I'll see the shadow of the pencil in that figure, like the spider veins. And I'll just rotate it around until I find the place where the rings are all bunched up and close together. And then that will be close to one of the collimation screws at the bottom of the telescope where the primary mirror is. There'll be a screw down here that this will be somewhere close to. And that's the first collimation screw that I'm going to want to touch. Back to shiny screen. Okay, so I'm going to find whatever one of the collimation screws lines up with that area in here. And that's the first screw I want to touch. And once I've located that screw, I'm going to just turn it a quarter of a turn, just a little bit, a quarter of a turn. And then you just repeat this whole process. You recenter the star, check the collimation again, and keep doing this until you get your pretty evenly spaced rings all the way around. And then you're done. You're collimated.
I have a question.
Go ahead.
Which way do you turn that screw?
Well, if you turn it the wrong way, it'll get worse.
Okay, in other words, the scopes aren't standardized. Is that correct, or are they?
They're not. I mean,
okay.
In
just take
cases,
that one and turn it slowly and forward.
You can't tell which way the mirror needs to go, in or out.
Gotcha. Okay.
So you just try one way, and if it doesn't work, you go back the other way.
Gotcha. 10-4.
It's a trial and error thing, and the reason you try to find the screw that's closest to that area, because chances are your collimation probably got knocked out of collimation because you bumped the scope. Okay, something like that happened to it, and usually when that happens, one or two screws will get a little loose. They'll change their position on the threads or something. So the area where the rings are really close together is usually lined up with one of the screws, because usually one of the screws is moved when you bump the telescope. That's usually what happens. Okay, so that's why I do it that way. So, and it's trial and error. Like I said, I don't know. You just take your choice. Turn it one way, it gets better. Turn it the other way, it gets worse. You just keep doing this until you get your good collimation. Okay.
Right. So I take it then we don't know which, like for instance, generally, here's an assumption, and it may be wrong. If I was to turn the screw to the right, clockwise, generally I would think that would tighten things up. So I would expect that to pull the mirror in the tube closer to the back of the tube. Or maybe not, but there's no standard one way or the other, correct?
No, there isn't really a standard, but I think you're right. I think for the most part, if you turn the screws clockwise, you're tightening them. You're pulling the mirror in.
Right. Okay.
But I don't know whether that makes the collimation better or worse.
Yeah, I was just curious, because I've only done it once, and I already picked up something good in your little description. But having done it a number of times, I was wondering if you were familiar with certain scopes, if it tends to pull the mirror towards the back or not, at least on that screw.
When I get to, I've got some images of some Newtonian reflectors.
Okay.
You can see the screws, and definitely for those, turning the screw clockwise will tighten it.
Okay.
The only thing I don't know is how does that work on the secondary on a Schmidt-Cassegrain. It might work differently. I don't know.
I get that.
So, but it's just trial and error. If you do it one way and it makes it worse, then you need to go back the other way.
Okay. Thank you.
Yeah. And one thing you always have to remember is after you've changed your collimation, you are definitely going to have to realign your finder scope, because you've changed the tilt of the mirror. It's no longer your finder scope is not going to be lined up anymore. You're going to have to realign your finder. Always remember that. I always have to remind myself that, because I have forgotten to do that on numerous occasions, and then I wonder why when I point at something that ain't in there. The finder, I'll have it dead center on the finder and the object isn't there. It's like, okay, wait, I just collimated it. Oops. Forgot to realign the finder. Yeah, you have to do that. And it's surprising how much your finder can be off from just a quarter turn of one of these screws. It can be so far off that you're not in the field of view anymore. Okay, so Schmidt-Cassegrains, I actually think are the easiest telescopes to do the collimation are, even though it's a very complex telescope. If you look at the picture, there's the general light path, and the primary mirror slides back and forth on the baffle tube there in the middle, and there's a corrector plate, and the only thing you can adjust is the secondary mirror. So if you look at the secondary mirror on the outside, you'll see the 3 collimation screws circled in red. And on most secondaries for Schmidt-Cassegrains, there's also that central screw. Don't ever touch the central screw. That's what holds the secondary in place. If you loosen that, your secondary mirror is liable to go falling down into the inside of your telescope, and that would be very bad. You'd probably break the main mirror, and who knows what else you'd do. Back in the old days, you also had another problem. 30, 40 years ago, Celestron used to their main mirrors would be ground to like plus or minus 1/10 wave, okay? And then the secondary mirror, they would actually grind it in such a way that bumps or pits in the main mirror would be countered by a similar bump or pit on the secondary mirror, so they could get actually they advertised that they used to get plus or minus 1/30th wave with the combined optics, which meant that you didn't dare touch the center screw, because the secondary mirror, if you loosen that secondary screw even a little bit, the secondary mirror could rotate on its mount, and that would of course unalign all those little bumps and pits that they had lined up so carefully. I don't know if anybody still does that. I don't think they do, because I think now they just grind the mirrors so much better than they used to. So I don't think that kind of correction is necessary. So I don't think it matters if you rotate the secondary mirror anymore. Oh, pardon me. My annual security check is coming up. You're not going to do the scan now. Okay. But still, you don't want to mess with that center screw, because if you happen to loosen it too much, the whole secondary mirror cell could fall right out of its holder. But the 3 collimation screws are those 3 screws around the perimeter. And so those are the 3 screws you want to adjust. And the reason I say Schmidt-Cassegrains are easy is when you're holding your pencil or your chopstick over the front of the scope, and you find the place where the rings are closest together, well, you're like pointing at one of those screws. I mean, the pencil is going to be right there on top of one of those screws, or really close to one. So you're going to know exactly where to take your little Allen wrench and twist. I noticed that a lot of the newer Celestrons and some of the other makers of the Schmidt-Cassegrains, they now put a plastic cover over all of those screws to protect them, I guess, from getting touched accidentally. So obviously you have to remove the cover when you're doing your collimation, but that's no big deal. Okay, so now we're going to talk about the reflector telescopes. There's basically two types. There's Newtonian and Cassegrain. You basically use the same procedure for both of them. In both cases, you've got a secondary mirror that's in the tube, and there are often, as you notice in both of these figures, there's again, just like the Schmidt-Cassegrain, there's a center screw, which is like here. And in this case, this is a home-built Newtonian. There's the big center screw there. And then there's usually 3 screws around the outside. There's that one. There's 2 more over here and over here underneath the spider. Those screws you are not going to use for collimation. You do not touch those because those screws are usually set in the factory, and those screws are set there to give that mirror the proper tilt, either the 45-degree tilt for a Newtonian telescope or a 90-degree tilt if it's a Cassegrain. And you don't want to ever touch those because that's just going to change the tilt of the mirror, and that's really not going to do anything for your collimation. Usually factory set, and usually don't ever have to touch those for the lifetime of the telescope unless you really, really bang it. What you want to use for collimation are the screws at the back end of the telescope. So the primary mirror is mounted in a mirror cell that's mounted into the tube. And every primary mirror I've ever seen on a Newtonian or a Cassegrain telescope has 3 collimation screws at the back of the scope. In this case, there are those 3 Phillips head screws that I've got marked in red. And this view here on the right, you can see that the Phillips head screw is actually got a spring on it. It's spring loaded, and that's so that it keeps tension on the mirror cell. So when you tighten it, you turn it one way, it pulls the mirror cell back. But if you loosen the screw the other way, the spring will push the mirror cell out. So that's how you adjust it. A lot of these mirror cells have locking screws. That's what these other 3 screws are. That's just what you do is when you want to do the collimation on the scope, you loosen the locking screws out. So it gives you some wiggle room to move the mirror cell back and forth. But then once you get your collimation set the way you like it, you tighten those screws back down, hand tight only, because if you put too much tension on them, they're actually going to push the mirror cell out and you're going to ruin your collimation. So you just hand tighten them so that they'll hold the mirror cell in place. Even if one of those springs were to break or something else were to happen, the 3 tightener screws, the 3 locking screws would keep the mirror from jiggling around too much. Here's another. This is that homemade telescope that I showed you a little bit earlier. And again, it's the 3 screws, the 3 collimation screws are around the perimeter of the mirror cell. And in this case, they've got wing nuts on them. But again, right here, you can tell in this image, it's got a spring on it. So you tighten the wing nut one way, it pulls the mirror cell back, and loosen the wing nut, and the spring will push the mirror cell out. And that's how you do that. And you'll see the same thing on a Cassegrain telescope. There'll be 3 screws somewhere around the perimeter of the mirror cell that you'll be able to adjust. Now, Dobsonians are a little bit different. A standard Dobsonian, which has a solid tube, for example, not a truss tube. Again, it'll be just like a regular Newtonian or Cassegrain. It'll be like a Newtonian, regular Newtonian. You'll have the mirror cell at the back of the tube, and there'll be the 3 screws there to adjust the mirror. But truss tube Dobsonians are a bit different because a truss tube Dobsonian has these bearings here and here. These white things are the bearings for altitude, for the altitude movement of the telescope. The thing sits right at ground level. The mirror is right down on the ground in a mirror box, basically, that's only a couple inches off the ground. So it's not very practical to put the adjustment screws at the back of the mirror cell. They'd be impossible to reach while you're using the telescope because the mirror box is virtually on the ground. So instead, what they do for truss tubes is they have the mirror cell sitting in a box, and it's mounted on 3 adjustable clamps or whatever you want to call them inside the mirror box, and you adjust the tilt of the mirror cell by changing the tilt of those 3 pillars or whatever they are that support the mirror cell that are in the box. And so here they are here. These are the 3 collimation screws for the telescope. They're in here. They're inside the mirror box, but you don't reach them from underneath. You have to go in through the tube. And this is a truss tube, so it's not a solid tube. So they usually give you a special tool to do this, which looks like this. It's got this end here is what goes into the collimation screw in the box, and you take this and you go in between a couple of the truss supports on the truss tube, and you stick it down there and you twist it one way or the other. And you can actually do this while you're looking through the telescope through the eyepiece up here. You can hold this thing and turn it one way or the other to adjust the collimation screws. Okay, and that's actually the end of my presentation, actually. That's the last slide. Any questions on this?
Well, I don't have a question, but on the SCT that I have,
Yeah,
there's the 3 screws that are up front on the secondary. I
yeah,
always had trouble getting a little Phillips screwdriver, finding that screw and trying to adjust it. And I found there's something called Bob's thumbs, which you replace those screws with
yeah.
thumb screws. And that's what I did on mine. And it makes things a lot easier. I don't have to be hunting because I just know where the 3 screws are. And just with my hand, I'm able to adjust it that way. So that's a little modification I made to mine, and makes things a lot easier for doing collimation.
Yeah, and that's fine. That works. Absolutely. On my Meade, on my Schmidt-Cassegrain, they're Allen head screws. So there's a little Allen wrench that you use, and it is really little. And I have it tagged, so I know exactly which Allen head wrench to use. But in the case of my Schmidt-Cassegrain, the collimation, I usually only have to do it once or twice a year.
Why are you being so
So I didn't think it was worth it to put the Bob screws in. I could have done it, and that's fine. You do it for yours, that's great. And I know a lot of people who like doing that, and that's probably not a bad idea, you know. Especially if you don't like to fiddle with that thing in the dark with a red light. It's a lot easier to deal with a Bob screw than, like you said, finding a little Phillips head or finding a little Allen wrench. You're right, it's a lot easier if you can grab it with your fingers and turn it. You're correct about that. So that's not a bad idea, and I would have no problems with anybody doing that for their telescope. I think that's probably a good idea, actually. Now that I think about it, maybe I should do it.
Yeah, then you'd have to mess with a screwdriver. My worry was dropping it and have it fall right on the glass up front and messing it up. And it was only $20, so I figured, okay, $20, I can deal with that.
Yeah, so, you're right about that. I always worry about that when I'm doing mine with the little Allen wrench. Yeah, because it's kind of hard to hold and play with, and I'm always worried that it's going to slip out of my fingers and hit the corrector plate. It's never happened to me yet, but I always do worry about that. That's not a bad idea. Get the little bob screws for your secondary.
Yeah, I think they're called Bob's thumbs is what the name if you
Yeah,
look it up
I've
on,
seen it
on Google.
before.
Yeah.
I've actually ordered something from them before for a different telescope. But yeah, I think it's a pretty good recommendation.
Yeah, that worked. Now I did get one of those laser collimators for my original 5-inch reflector, and I always had trouble with it. So that's one thing that, yeah, it was nice and sounded fancy, but I could never really get it to work. So it's like, okay,
I've seen these things work, and I've seen them work really well. Okay. But like you, I've also known a lot of people who just can't quite get it to work the way it's supposed to for one reason or another, or it doesn't give them the results they want. And so, you know, I'm not going to say necessarily don't go out and get them if you think you want to and you think you can make it work. I know that those laser collimators or those collimation eyepieces will probably give you a more accurate collimation than you would get just by star testing. But I honestly think you can do a pretty good job with star testing. I mean, I think if you center that star up in your eyepiece and then you put it way out of focus to where it's really big and you see all those rings, you can really tell when it's out of collimation, even a little bit. You can really tell because you'll see the rings closer together on one side than they are on the other. And you can do, I think, an amazingly good job of collimation without using external devices. If you've got them and they work, great. I'm not ever going to buy one for any of my telescopes, but if you want, that's, you know, I'm neutral on those things. But like you, I've known people who couldn't get them to work or just never worked the way they wanted. But I've known other people who've got laser collimators and swear by them. So, yeah, your choice.
So Doug, Jay Orchard has a question about if you buy a used Cassegrain and you successfully collimate it, does that mean the telescope is okay?
Say that again.
The question is, if you buy a used Cassegrain, would a successful collimation of the optics mean that the telescope is quote unquote okay?
What do you mean by okay, I guess is what I would ask. If you buy a telescope and you check the collimation on it, and the collimation looks good, meaning the rings are all evenly spaced and it looks like it's good collimation, then it's probably in reasonably good shape, at least optically. And it would also have to be in good shape. I mean, the mechanical collimation would have to be good too, otherwise it wouldn't collimate optically. I mean, if your mirrors are not lined up or the mirror is not tilted at 90 degrees or 45 degrees, the secondary mirror is not tilted right, you're not going to get an optical collimation. It's not going to work at all. But if you can get a good optical collimation on a telescope, it's probably in good shape. And I mean, there could be other things wrong with it. You know, I mean, there could be things wrong with the mount. There could be things wrong with the focuser. There could be things, you know, there could be other issues with the telescope. But if you get a good optical collimation, that usually means the optics are good.
Yeah, when I bought my SCT, I got it from a guy in Florida who had moved from California, and he had a condo and he had like 6 telescopes, and he offered it for sale on Astromart. And I thought about it, and I said, well, this guy probably has telescopes. He probably takes good care of them. So I didn't really worry about it being a good or a bad telescope. And when I got it, it's been working just great, you know. So it's not like a car where all sorts of things can go wrong. There really isn't that much. So I didn't really worry about buying a used telescope. You know, it wasn't that big of a deal to me.
I have no problems in buying used telescopes either. People tend to take care of them.
Right. Yeah.
And like you said, there isn't a whole lot that can go wrong. I mean, perfect example are the telescopes that were stored in the barn. We had a couple of Newtonian reflectors that were stored in the barn, have probably been there for 20 years without anybody touching them. I brought them home, cleaned them up, cleaned the optics, put them back together. They're as good as new. In every sense of the word, they're as good as new. We've got a Criterion clock drive out there that's got to be 40 years old. I took that apart. The thing was as clean as a whistle and works perfect. There isn't a whole lot that can go wrong with most telescopes. Now, I think, that being said, the more modern telescopes that have all the fancy computer stuff in them now, there is more that can go wrong with those because of the complexity, and they have the computer chips in them and the clock drive and all that. And there's more things that can burn out or go wrong. That old Criterion clock drive had no chips in it or anything. It just had an electric motor with gears that drove it at the correct speed. There was no fancy anything, and you adjust it. You can change the voltage going to the motor with the control, so the motor either speeds up or slows down based on that. The modern ones, they have computer controls in there they have circuit cards in the clock drives. My Meade Schmidt Cassegrain, which is pushing 30 plus years old now, even it has a circuit card with a chip and some other things on it, for controlling the speed of the clock drive. So if that circuit card ever decides to go bad on me, then my clock drive that's it, gone. So the newer telescopes do have more things that can go wrong with them, so to speak, but I still think they're incredibly reliable. I think they last forever, unless you really mistreat them.
Now, you had mentioned before that the club has a Mazatov.
We have the optics for a 14-inch Mazatov. We have a primary mirror. We have a 14-inch Mazatov corrector plate, and we have in this case, it's not a silver spot on the corrector plate. It's an actual secondary mirror that fits in a hole that was put in the corrector plate. So it just goes in there. We do have the optics for that scope. Now, we don't have a mount for it. We may or may not have a tube for it. I'm not sure. We do have the mirror cell for holding the primary mirror. And I think we have a mirror cell that holds the corrector plate, but I'm not 100% sure until I actually try to put it together. So we've got the basic components to put together a 14-inch mock. And I told Terry Lappin that what I might do is start going out to Timpa and actually seeing if I can assemble the optical tube assembly for that mock. And then if we can ever put that thing together and get it working optically speaking, then that would be something that maybe we could build a mount for and build a roll-off, roll-on thing for out at Timpa and have a nice 14-inch mock, which would be a really nice telescope to have.
Thank you very much, Dan.
We do have the main pieces for it.
Any other questions?
All right.
Great presentation, Doug. Thanks.
I wish more people would have showed up tonight.
We actually had double the crowd we normally do. So
yeah, I still, there's a lot of people I wish, like Kay Lehman. Is she here? No. She should learn how to do this, and other people should learn how to do this. It's actually easy.
I think she went to we had when Dennis McMacken gave a Collimation talk several years ago.
Yeah, she probably knows by now.
Well, she probably knows but forgot. Anyway, So I'm going to end the recording here so I can transition over to something that I want to show off, which I'm not quite ready to have persisted.